The next and final speaker that we have is Xuqian Li from University of Queensland, speaking about mental health in the UK Biobank, an updated roadmap for brain behaviour associations.
Okay, hi everyone, my name is Michelle Li, and I'm a postdoctoral research fellow at the University of Queensland. So today I'm going to present our work that's kind of mapping brain mental health associations using the UK Biobank dataset. So many of us have tried to figure out the neural correlates of mental health conditions using brain-wide behavior association analysis, but how strong those associations really? So the UK Biobank, if you haven't heard about it, is a longitudinal dataset that includes over 500,000 people, which gives us an incredible opportunity to estimate the brain mental health associations at scale. So many participants in the UK Biobank have completed brain MR scan and also online questionnaires. So this leads to thousands of image-derived phenotypes and also hundreds of mental health derived phenotypes. So what has been missing is a systematic overview, so a way to identify which brain mental health association consistently show up, so how strong those effects really are and how they hold up when we kind of consider the repeated measures over time. So in this project, we aimed to build a comprehensive, up-to-date roadmap of brain mental health associations in the UK Biobank. So first of all, we want to define our cohort of interest. So we focused on participants who have completed 4 data collection waves. So this includes the initial imaging visit in 2014 and the repeat imaging visit in 2019, where participants went to the assessment center, they complete the MRI scans along with touchscreen questionnaires where there are mental health related questions. This also includes 2 large online surveys. So the first one is the mental health questionnaire surveys introduced in 2016, and the second one is the mental well-being questionnaires introduced in 2022. So this led to a cohort of over 4,900 participants. So to make sure that we could assess the robustness of the associations, we split the sample into 2 subsets of roughly equal size, a discovery subset and a validation subset. So after doing all this pre-processing and the confounding, we ended up with over 4,500 imaging-derived phenotypes covering all MRI modalities except for fMRI, and as well as 356 mental health phenotypes. So we also want to take advantage of the longitudinal design of the UKB, so we also identify repeated measures over time. So in total, there were over 2,200 image-derived phenotypes and 95 mental health-related phenotypes. And so in order to estimate the univariate effect size, we performed Pearson's correlation as well as the repeated measures correlation between each pairs of this kind of phenotypes within each subset of samples. So this resulted in over 1.6 million Pearson's correlations. So as you can see in the left panel here, the distribution of effect sizes is bell-shaped and centered around 0 and suggesting there are both positive and negative associations. So most of these correlations are quite small. So in the top middle panel here, you can see that the median absolute effect size is around 0.02, but thankfully, some associations stood out. So the top 1% of absolute correlations are greater than 0.21. So looking at the Manhattan plot here of p-values in the top right panel, we identified 670 correlations that were significant in the discovery set after FDR corrections. And also, I want to mention that there were about like 350 correlations that were kind of reproduced in the validation set. And also, as you can see on the bottom right panel, there we are plotting the differences between the effect size of the discovery set and the validation set. So on the x-axis is showing the effect size of the discovery set. On the y-axis, we are showing the difference between the two sets. So you can see there's a diagonal pattern here. So it's kind of showing that when you have larger effects in the discovery sets, there are kind of larger difference between the two sets. So compared to the Pearson's correlations, the distribution of more than 200,000 repeated measures correlations was less symmetric and skewed toward more positive associations. So the median absolute effect size was 0.04, and the top 1% of effects were greater than 0.41. So in terms of statistical significance, 45,000 repeated measures correlations were significant after FDR corrections. And I want to mention again, there were like 37,000 of those were also reproduced in the validation set, which is quite promising. So the scatter plot of replicability here is showing a kind of compact lens shape around the line of zero on the y-axis, which is showing that there is greater agreement between the discovery and validation set in terms of effect size. So there are like many results here. So to help visualize and compare results across different mental health and imaging categories, we created a set of radar plots. So each trying to capture a different aspect of the associations. So including availability, which is showing the numbers of variables in each category. So these are supposed to be radar plots, and so basically the idea is that we created this kind of framework. So the first one, we are showing the availability, is showing like how many variables you have in the UKB in terms of different category. And then the second one is the typical effect size. So when you're considering the brain behavior associations, you want to see what's kind of typical. And this is defined as the median Pearson's R correlation. And thirdly, we also want to look into what is the large effect. So here is showing a radar plot of top 1% Pearson's correlation. And finally, we want to show the replicability, which is, again, kind of defined by the proportions of the significant effect that has been reproduced or validated in the validation set. So maybe we can just walk through a user case and just imagine that there is a nice looking radar plot here. So if you guys just found it a bit weird, just please come to my poster. But now I just want to finish up the talk. So imagine that you're a researcher interested in finding which mental diagnosis might have more reliable brain biomarker, and you don't necessarily to know all the things about neuroimaging. So what we can do with the radar plot is that we want to look at the availability in the UKB. So this radar plot is supposed to show the difference, shows the 6 distinct mental health disorders, which is included in UKB. So here, including depression, eating disorder, substance use, and PTSD, and also non-specific category of mental disorders. So what it was supposed to show is that the depression kind of stand out because it has the largest numbers of variables available in the UKB. So it's supposed to, this one should be the depression. And so the next one, okay, this one looks better. So the next thing is that so it seems that depression seems to be a good starting point. So next, we can look at the typical effect size. So for depression, the median absolute effect size is about 0.01. It's kind of small, but it is kind of comparable to the other kind of disorders which is available in UKB. As you can see, PTSD and also non-specific disorder have similar and comparable effect sizes. And what's notable is that eating disorder and bipolar disorder showing higher typical effect size compared to the other mental disorders included in UKB. And so thirdly, of course, some questions tend to show stronger associations than others. So it is also useful to look at the large effect, which is again defined by the top 1% of the effect size. So for depression, we have like 0.1, which is okay. And it is, you can see, when we put this into context, we can see it is comparable to other mental health disorder. And what is kind of, again, quite striking is that the top 1% of absolute correlation of eating disorder now is reaching over 0.6, so it is something important to consider. So finally, it is also crucial to ask whether these associations replicate in different sample sets we have. So for depression, the results are encouraging because we see that depression is actually the one that has the highest numbers of significant association that has been replicated in the validation set. But something need to keep in mind is that the replicability, or say the proportions of replicated association, is poor or low for like anxiety, bipolar disorder, non-specific category, and PTSD. So something to bear in mind when we are planning future study or future analysis with the UKB datasets. So this is just one example of how the rater plots we created can be used. So in fact, the UK Biobank dataset includes variables for a range of change diagnostic features, and also we have like environmental factors. And also, all this kind of things and results can be grouped into imaging modalities. So you can see here we have like diffusion, MRI to T1 and T2 structural MRIs. So the thing is that I don't have enough time to show all the results here, but in order to serve both the psychology and neuroimaging communities, we have this kind of web-based tool which basically allows us to visualize the results in the context of rater plots with all different possible combinations. So you can, let's say you're interested in eating disorders and diffusion imaging related phenotypes, you can just click on button and then generate the plot, and then it will give you this beautiful looking rater plots. And so to conclude, we hope this work can serve as a practical roadmap for researchers. It provides a clear overview of effect size of brain mental health associations in the UKB and help guide the decision about which variables and analysis we should focus on. And finally, hopefully provide a realistic benchmark to support power calculation when planning future study. So again, please come to my poster and scan the QR code here for the website for the actually good-looking rater plots. All right, so before I wrap up, I would like to thank Lena and Sarah for their valuable contributions to this project, and also a big shout out to everyone in the lab, which kind of provide like valuable feedback and support throughout. So thank you, guys. Thank you.
Thank you so much, Dr. Li. Very sorry about the technical difficulties with your slides. Fantastic work. Yes, please go to the posters of our speakers today. Let's thank them all for their hard work, and thank you so much for attending. Enjoy the rest of the meeting.